We're going to talk in this video about chemical equations and how to balance them. So chemical equations tell us the reactants and products that are present in a chemical reaction. And they also describe the proportions of reactants and products in a chemical reaction. So if we have our generic reaction, we're just going to have two generic compounds here, A and B, which form C and D. A and B, the substances that get consumed during a chemical reaction, are our reactants. And C and D, the substances that get formed in a chemical reaction, are our products. In a chemical equation, sometimes you will also see the physical state of the products or the reactants. So you will see those written in parentheses next to the compound. So for example, S is solid, L is liquid, and G is a gas. AQ refers to an aqueous solution. So an aqueous solution means that it's dissolved in water. To give you a few examples, if we look at the first reaction listed here, SO3 is a gas. So SO3 here is a gas. It reacts with water, which is a liquid, and forms sulfuric acid, which is also a liquid. In our second equation here, we have Fe2O3. That is a solid. That reacts with sulfuric acid, which this time is an aqueous solution, meaning the sulfuric acid is dissolved in water. And that reaction produces water, which is a liquid, plus iron sulfate, which is an aqueous solution. Now, when we do a chemical reaction, we have to remember the law of conservation of mass. The law of conservation of mass tells us that the sum of the masses of the reactants in a chemical equation has to be equal to the sum of the masses of the products. So you can't lose matter. You end up with the same amount of matter that you started with. You only change what you have. So you react your reactants, they're going to react together. They're going to form two or more different products, or sometimes only one product. So you rearrange what's bonded with what's, and you get different compounds, but you do not lose any mass. There's actually an experiment that we do sometimes in labs where you react baking soda and vinegar. Since baking soda and vinegar are both something we can measure the mass of, we can measure the mass of the vinegar even though it's a liquid. We can weigh an empty graduated cylinder or beaker and then pour our vinegar into it, or you can use the tare function on the balance and zero out the balance and then pour your liquid into a beaker, your vinegar into a beaker, and you can measure the mass of your baking soda. So you know the masses of your starting products, and then what you do is you react them. That forms sodium bicarbonate dissolved in water, and then it also forms carbon dioxide. Of course, carbon dioxide is a gas, and we're doing this in an open container, so it's going to escape into the air. But you know the mass of baking soda and vinegar you started with, so then you measure the product the mass of your product, and then you subtract the mass of your product from the starting mass of your reactants, and you can determine the mass of carbon dioxide that was produced. So we're going to talk about here how to balance equations. Before we actually do one, let's go over a few strategies. one thing I suggest you do, if you have an element that's present in just one compound on each side, start with that. A lot of times it's more complicated when you have an element that's present in more than one compound on either the reactant side or the product side. So if you take care of the ones that are present in only one place first, sometimes you can simplify your life a little bit. You want to balance anything that exists as a free element last. So a good example of this is in some reactants we will have O2. We're going to talk about a specific type of reaction where you will always see O2. If you have something like that, leave that alone until last. A lot of times, if you balance everything else in your reaction, then once you get everything else balanced, it works out so that you just have to put a coefficient in front of the free element. So you make your life a little bit easier because all you have to do is figure out what you need to multiply that free element by, and you're done. If you have polyatomic ions, balance those as a unit. Okay, the number of each element that's in a polyatomic ion is not going to change from side to side. So just balance the whole ion as a unit, and that's less work for you to do. Then when you're done, you want to check that you have the same number of atoms and the same, if you have charges in the reaction, you want to make sure you have the same total charge. We don't deal with a whole lot that have charges at this point, but just something to be aware of. But you definitely want to make sure you have the same number of atoms on each side. So let's take an example here. We have CH4 plus NH3, and that forms HCN plus H2. So what I like to do when I balance reactions is I like to make a table of what elements I have. The reason that I do this is you have multiple elements on each side, and you're trying to get everything balanced. Especially when you get up to reactions that have multiple, that have 4, 5, 6 elements or so on, that starts to be a lot to keep in your head. So I like to just make a table so that all the counting is on paper and I don't have to keep track of things in my head. So in this reaction I have carbon, nitrogen, and hydrogen. And make sure if you use the table method, keep your elements in the same order on each side. Because what we're going to do is compare across to see how many of each element we have. And if they're not in the same order, then that makes it a little bit harder to do the comparison. And the entire purpose of the table is to make our lives a little bit easier. Now, if you don't like the table, if you prefer to keep track of it in your head, and you can keep track of all those numbers, that is perfectly fine. This is just a method that I use. So, carbon, we only have one of those. Nitrogen, we only have one. Now, hydrogen, we have in 2 places. So, I've got 4 in the CH4 and 3 in the NH3, which means that I've got a total of 7. If I go over to the product side, I have only 1 carbon, I have 1 nitrogen, and I have 1 carbon here in the HCN, and 2 in H2, so that's a total of 3. Now, we have hydrogen in 2 places on the reactant side. So remember what we said, to start with elements that are only in 1 place on each side. So we're definitely not going to want to start with hydrogen. And we also have hydrogen as a free element over here on the product side. So I'm going to start with either carbon or nitrogen. But if I look down at my table, I have the same number of carbons on each side and the same number of nitrogens on each side. So those are already balanced. So then that brings me back to hydrogen because that's the only thing left that's not balanced. Now I have 7 hydrogens on the reactant side and 3 on the product side. So I probably want to get more of them on the product side. And if I look, I have it in two places. One of those places is with the HCN, and the other one is hydrogen by itself. So if possible, I want to balance this by changing the number of hydrogens by itself. Because if I change anything with the HCN, then that's going to change carbon and nitrogen. And if I change those, then I have to go back and change something on the reactant side, and then that messes up the hydrogen, and it's just going to be a back and forth. So it's probably much easier to just deal with the H2. Now, I want to get 7 of these, and right now I only have 3. So I have 1 here, so that means I need to find some way to make 6, a total of 6 from this H2, so that 6 plus 1 is 7. So what I can do, I have 2 here, so if I put a 3 here, 3 times 2, because we multiply the coefficient times the subscript. So 3 times 2 is 6, plus 1 hydrogen from the HCN gives us a total of 7. So that balances our reaction. So let's try a couple more of these. We have aluminum, bromine, and potassium in this reaction. Potassium. So right now I have 1 aluminum, 3 bromines, and 1 potassium. So the only thing looking at my table that's not balanced right now is the bromine. I have 3 bromines on the reactant side and only 1 on the product side. So I'm going to put a 3 here in front of KBr. Now, the KBr is an entire compound. So I can't get 3 bromines without also changing the number of potassiums. You can't stick coefficients in the middle of a compound. Yeah, I see students try to do that sometimes, and you can't do that. You have a whole compound, and this molecule exists as an entity. You can't break it apart. So the only thing we can do is to have more molecules of KBr. So that changes the bromine to 3, but that also makes me have 3 potassium. But fortunately that's a simple fix because we only have potassium in one place and we have it by itself. So all I have to do is stick a 3 in front of that potassium, and now my potassium is balanced. So let's look at the reaction here on the bottom. And I'm going to move my table up here so that I'm not running into the bottom of the screen. Oops, that's supposed to be fluorine. So if I count these up, I have 1 iron, 1 oxygen, 1 palladium, and 2 fluorines. I have 1 iron, 1 oxygen, 1 palladium, and 2 fluorines. So this one is already balanced. Okay, let's look at a few more here. So we have CO, Br, Ca, calcium, and since sulfate stays together, I'm going to balance that as a unit. So I'm going to do the same thing on the other side. So if I go through and count this up, I have 1 cobalt, 3 bromines, 1 calcium, Since sulfate does not have a parenthesis around it with a subscript on the outside, that means there's only one sulfate. Cobalt, I have 2 of those. I have 2 bromines. I have 1 calcium. And actually, cobalt's over here, so yes, I do have 2 cobalt. And then sulfate, I have 3 of those. So I've got a couple things that are not balanced. My cobalts and bromines are not balanced, and my calcium is not balanced. My calcium is balanced. My sulfate is not balanced. So we need to pick somewhere to start. So I'm going to start with cobalt and put a 2 here. Now, you could start in different places. You just have to pick somewhere to start. So I'm just going to go ahead and pick the cobalt since that's listed first and it's only in one place. So if I change cobalt, that gives me 2 cobalts. 2 times 3 is 6. So that gives me 6 bromines, which means that now I've got to change my bromines over here. So if I want to get 6, that means I need to put a 3 here, which gives me 6 bromines, but that gives me 3 calciums. So now I'm going to balance calcium, and I can balance sulfate at the same time by putting a 3 here. So this gives me 3 calcium and 3 sulfate. So I'm going to make a list here of what I have. And notice I'm keeping the cyanide, which is one of your polyatomic ions, and the carbonate together. Okay, those stay together as a unit, so we're just going to balance them as a unit and make our lives a little bit easier here. So if I go through and count this up, I have 1 sodium, 1 cyanide, 1 copper, and I have 1 carbonate ion. On this side, I have 2 sodiums, and I have 1 carbonate ion. I have 1 copper, and I have 2 cyanide. So the only thing that's not balanced is the sodium and the cyanide. So if I put a 2 here, that balances the sodium and the cyanide. So another type of reaction, or a specific type of reaction, is a combustion reaction. So combustion reactions are reactions with oxygen in the presence of heat. So we have some compound, or sometimes it can be more than one compound, in the presence of oxygen under enough heat, they will undergo combustion, or in other words, they will burn. So for example, here we have sulfur dioxide in the presence of oxygen, and if we put this under enough heat, this will undergo combustion and we get sulfur trioxide. Same thing here, we have CH4, which is methane, with oxygen. Whenever you have a hydrocarbon, which is a compound that only has hydrogen and carbon in it, the products of that reaction, when it burns with oxygen, when it undergoes combustion, will always be carbon dioxide and water. So let's check to see if this last combustion reaction was balanced. And if it's not, then we're going to balance it. So we have carbon, hydrogen, and oxygen on each side. So we have 1 carbon, 4 hydrogen, and 2 oxygens. So our carbon is balanced, but our hydrogen and our oxygen are not. So remember, whenever we have something as a free element, we're going to leave that to last. So oxygen here is an example of a free element. So we're going to start with the hydrogen, and we're going to put 2 here. So 2 times 2 gives us 4. 2 times 1 is 2, plus 2 over here is 4. So if I stick a 2 here, that gives me a total of 4. So now my reaction is balanced. So let's try one more example here. We have C3H8 plus O2. So we have carbon, hydrogen, and oxygen again. We have 3 carbons, 8 hydrogens, and 2 oxygens on the reactant side. So we're going to start by balancing the carbons. So if I put a 3 here, that gives me 7 oxygens. And now I balance my hydrogen. That's 8. 6 plus 4 is 10. So if I put a 5 here, now my reaction is balanced. So we will get more practice with this in class. And I will see you there.